In this video and the next, we're going to continue familiarizing ourselves with properties of homomorphisms. All of the properties that we're going to talk about are fundamental. They're things that we use in this subject all the time, so it's important that we understand them thoroughly. Just to remind you of the properties that we've covered so far, if phi is a homomorphism from G to H, then first of all we proved that phi has to map the identity element in G to the identity element in H. Then we proved a property that we called 1b, but 1b is contained in property 1c. And 1c says that for any g in G and for any integer n, phi of g to the n has to be phi of g to the n. 1b, remember, was the special case of this property when n is equal to -1, and it said that phi of g inverse is equal to phi of g inverse. The next property that we proved was that the image of any homomorphism has to be a subgroup of the codomain. And after that, we proved that the kernel of a homomorphism, which is the set of all elements of the domain which map to the identity in the codomain, has to be a subgroup of the domain. And finally, the last property that we proved in our video about basic properties of homomorphisms was that if phi happens to be an isomorphism, so that it's a bijective homomorphism, then its inverse function is also an isomorphism from H back to G. If you need a refresher on any of these properties or you want to see some examples, you can look back at our video on basic properties of homomorphisms. The first collection of new properties that I want to talk about in this video give us information about what homomorphisms and isomorphisms do to elements of a given order. So the first property here, which I'm going to call 5a, says that if little g is an element of the domain with finite order, and if phi is a homomorphism from the group G to H, then the order of the image of the point little g has to divide the order of G. Now the proof of this one is not too difficult, so let's suppose that the order of our element little g is n for some natural number n. And let's notice that by property 1a, the identity element in H is equal to the image under phi of the identity element in G. Well, since the order of G is n, that means that the identity element in G is equal to little g to the n. But since phi is a homomorphism, by property 1c, phi of g to the n is equal to phi of g to the n. So now we have the equation that phi of g to the n is equal to the identity in H. And if you remember our video about cyclic groups, we proved there that anytime a power of an element is equal to the identity in a group, it implies that the order of that element must divide the power. So here that means that the order of the element phi of g must divide n, and that's exactly what we wanted to show. The next property that I want to prove, which I'm going to call 5b, is that if phi is actually an isomorphism from G to H, then for every element little g in G, the order of little g is equal to the order of phi of g. Now for the proof of this one, we're going to need to divide it into two cases. So first of all, let's consider the case when the order of the element little g is finite. In this case, first of all, by property 5a, we have right away that the order of phi of g must divide the order of G. And in particular, notice that that implies that the order of phi of g must also be finite. Well, now we can combine this with property number 4, which remember told us that anytime you have an isomorphism from G to H, the inverse function is also an isomorphism from H back to G. Here we can apply property 5a again, but this time to the isomorphism phi inverse, allowing us to conclude that the order of phi inverse of phi of g, which is the order of G, divides the order of phi of g. But now we have two natural numbers, the order of g and the order of phi of g, and we know that the order of phi of g divides the order of g and vice versa, allowing us to conclude that the order of g must indeed be equal to the order of phi of g. So that takes care of the case when the order of the element little g is finite. Next, let's think about what happens in the case when the order of g is infinite. In this case, what we want to show is that if the order of g is infinite, then the order of phi of g is also infinite. And in order to do this, let's consider the contrapositive of this conditional statement. The contrapositive of this conditional statement, which of course is logically equivalent to the original statement, is the statement that if the order of phi of g is finite, then the order of g is also finite. So if we can prove the contrapositive, then we'll establish the original statement. Therefore, assume that the order of phi of g is finite. And now, arguing as before, since phi is an isomorphism, by property 4, we know that the inverse function is also an isomorphism. And if we combine that with property 5a, it tells us that the order of phi inverse of phi of g divides the order of phi of g. But phi inverse phi of g is just g, so this tells us that the order of g must divide the order of phi of g. Well, if the order of phi of g is finite, then that also forces the order of g to be finite. So that establishes the contrapositive statement and it also shows that our original conditional statement is true. That takes care of both the cases when the order of G is finite and when it's infinite, and it therefore completes the proof of property 5b. Finally, we have a property which I'm going to call 5c, which we can deduce very easily from property 5b. Property 5c says that if phi happens to be an isomorphism from G to H, then for every natural number n, the cardinality of the collection of elements of G with order equal to n is equal to the cardinality of the collection of H's in H with order of H equal to n. And this is true even if the sets on both sides of this equation happen to be infinite. As I said, the proof of this property follows very easily from property 5b, because since phi is an isomorphism, phi inverse is also an isomorphism, and combining that fact with property 5b guarantees that if phi is an isomorphism, then it's a bijection from the set on the left to the set on the right. Well, to say that two sets have the same cardinality is exactly the same as saying that there's a bijection between the two sets, so that completes the proof of property 5c. Now I'd like to give you some examples so that you can see how these properties might be useful. First of all, you might remember that back in our video about groups of orders 4 through 8, we mentioned that there are 5 non-isomorphic groups of order 8, and that 3 of them are the Abelian groups C8, C2 cross C4, and C2 cross C2 cross C2. Well, how can we actually see that these groups are pairwise non-isomorphic? First of all, let's gather some basic information about orders of elements in these groups. The group C8 is one that we understand pretty well, so let's choose a generator X for this group. Well then, the order of that element is 8, and we could also say more about the orders of other elements in this group, but this is all that we're going to need for the calculation that we're doing here. How about the group C2 cross C4? Well, let's choose generators for each of the groups in this direct product, say y1 for the group C2 and y2 for the group C4, so that the collection of all elements of the direct product is the collection of all ordered pairs of the form y1 to the I, y2 to the j, where I goes from 0 to 1 and j goes from 0 to 3. Now first observe that if you take any element of this group and you raise it to the 4th power, by the rule for the binary operation in the direct product of two groups, that just becomes y1 to the power 4i times y2 to the power 4j, which by properties of exponents is y1 squared to the 2i, y2 to the 4th to the j. I've written it this way because I want you to notice that y1 squared is the identity and y2 to the 4th is the identity, so that this element is really just identity comma identity, which is the identity element in the direct product. Since when I take any element of this group and I raise it to the 4th power, I get the identity in the group, that implies that the order of any element of the group must divide 4. Okay, well, let me collect one more piece of information here. If I take the element identity comma y2, of course I know from the previous calculation that its order must divide 4, but now I just want to convince you that the order of this element actually is 4, and that's pretty easy to do. When I take this element to the 1st power, of course I don't get the identity element, and when I square the element I get identity comma y2 squared. But since y2 squared is not the identity element in the second component here, that's not the identity element in the direct product either. So these calculations tell me that the order of this element is not 1 or 2. And since it has to be a divisor of 4, the only other possibility is that the order of the element is 4. I'll summarize those two pieces of information right here. The order of any element of this group must be a divisor of 4, and the element identity comma y2 is actually an element of order 4. Okay, now let's move on to the final group, which is C2 cross C2 cross C2. And once again, let's choose generators for the groups in each of the components of this direct product. If I choose my generators to be Z1, Z2, and Z3, then the elements of this group are all elements of the form Z1 to the I, Z2 to the j, Z3 to the k, where the I, j, and k now all run from 0 to 1. Well, similar to what we did before, think about now what happens when you take an element of this form and you square it. By the rule for multiplication in the direct product of these groups, this just becomes z1 to the 2i, z2 to the 2j, z3 to the 2k, which is the same as z1 squared to the I, z2 squared to the j, z3 squared to the k. And since z1 squared, z2 squared, and z3 squared are all the identity, this is just the identity element in the direct product. So this calculation now shows that every element of the direct product must have order dividing 2. Well, this is all the information that we need in order to prove that these three groups are pairwise non-isomorphic. Remember that if there were an isomorphism between any two of these groups, then that isomorphism would have to preserve the number of elements of any given order. But if you look at these three groups, the only group here which has an element of order 8 is C8. And that right away tells us that it can't be isomorphic to either of the other two groups, since neither one of them has an element of order 8. Therefore, we know that C8 is not isomorphic to either of those other two groups. And the only other pair of groups left to consider is C2 cross C4 and C2 cross C2 cross C2. But here you can just observe that C2 cross C4 has an element of order 4, but C2 cross C2 cross C2 does not. So by the same reasoning, that tells us that C2 cross C4 is not isomorphic to C2 cross C2 cross C2. And that verifies the claim that these three groups are pairwise non-isomorphic. Continuing with our groups of order 8 theme, let's now show that the two non-Abelian groups D8 and Q8 are non-isomorphic. So remember that D8 is the dihedral group of order 8, which has a presentation of the form group generated by R and S subject to the relations that R to the fourth is S squared as the identity, and Rs is SR inverse. We mentioned before in our video about dihedral groups that given these generators, the elements of the group are the identity R, R squared, R cubed, and S, SR, SR squared, and SR cubed. So now let's go through and think about the orders of all of these elements. The order of the identity element is 1, and it's easy to see that the order of R is 4, the order of R squared is 2, and the order of R cubed is also 4. Similarly, it's pretty easy to see that the order of S is 2. And we mentioned in a previous video that the order of each of the other elements is also 2. So to remember why that's true, think about, for example, if you take SR squared, which is SR times SR. Well, if you group together the R and the S in the middle here, and then use the relation that Rs is SR inverse, this becomes S times SR inverse times R, and now the two S's in the front multiply together to give the identity, and the R inverse R also multiply together to give the identity. So this is just the identity. And this argument shows that the order of SR is 2. Now, a similar argument shows that the orders of the other two elements here are also 2. So these are the orders of all of the elements in the dihedral group of order 8. For the group of quaternions, remember that we wrote it as plus or minus 1, plus or minus I, plus or minus j, and plus or minus k. And now, since 1 is the identity, the order of 1 is 1. And since negative 1 squared is 1, the order of negative 1 is 2. But the order of I turns out to be 4, and it's pretty easy to see why that's true. I squared is negative 1, and negative 1 squared is 1. So I to the fourth is 1, which means that the order of I must divide 4, but it's not equal to 2 and it's not equal to 1, therefore the order of I is 4. Now by an exactly analogous calculation, you can show that the orders of all of the other elements in the quaternion group are also equal to 4. And now we have all the information that we need in order to give a reason why these two groups can't be isomorphic. There's actually more than one reason that we could give here, but one thing that we can do is we can compare the numbers of elements of order 4. So in the quaternions there are 6 elements of order 4, but in the dihedral group of order 8 there are only 2 elements of order 4, and that tells us by property 5c that there can't be an isomorphism between these two groups, so they're not isomorphic to each other. Our next property, which can also be useful to determine when two groups are not isomorphic, is property 6. And what it says is that if you have an isomorphism from a group G to a group H, then G is abelian if and only if H is abelian. To say this another way, if you have two groups G and H which are isomorphic, then they either have to both be abelian or they have to both be non-abelian. To prove this, first of all, let's suppose that G is abelian and let's prove that H is abelian, and then we'll talk about how to prove the converse. So if G is abelian, then let's pick two elements H1 and H2 in H. And of course, what we'd like to show is that H1 times H2 is the same as H2 times H1. Well, since I have an isomorphism phi from G to H, I can choose elements G1 and G2 in G with the property that phi of G1 is H1 and phi of G2 is H2. Now think about what happens when we multiply together H1 times H2. H1 is phi of G1 and H2 is phi of G2, but since phi is a homomorphism, this is the same as phi of G1 times G2. And now I already know that G is abelian, so G1 times G2 is the same as G2 times G1. And now I can unravel these steps in the opposite order, first using the fact that phi is a homomorphism to write this as phi of G2 times phi of G1, and then recognizing that that's the same as H2 times H1. So what we've shown here is that for arbitrary elements H1 and H2 in H, H1 H2 is the same as H2 H1, and that's exactly what we need to show in order to conclude that H is an abelian group. That proves one direction of this property. To prove the other direction of the property, if we assume that H is an abelian group, then we can go through exactly the same argument, but this time using the fact that the inverse function of an isomorphism is also an isomorphism, and we can deduce in the same way that we did above, that G also has to be an abelian group. That completes the proof of this property. For an example of how this property can be useful, let's come back again to our 5 groups of order 8, and let's show that all 5 of these groups are pairwise non-isomorphic. Well, in examples 1 and 2 in this video, we already showed that the first 3 groups here are pairwise non-isomorphic, and that D8 and Q8 are non-isomorphic. So now we just need to think about whether or not any of these first 3 groups could be isomorphic to D8 or Q8. But by property 6, that can't happen because the first 3 groups here are all abelian groups, but D8 and Q8 are non-abelian groups. So that tells us right away that none of the first 3 groups can be isomorphic to D8 or Q8. And it finishes our proof that all 5 of these groups are pairwise non-isomorphic groups of order 8. Now, of course, at this point, we haven't really said why there can't be other non-isomorphic groups of order 8, but that's something that we're not going to try to deal with until later on. The final property of homomorphisms that I want to talk about in this video is property number 7, which says that if phi is an isomorphism from G to H, then the 2 groups must have the same lattices of subgroups. To be precise about what this means, it means that there's a bijective correspondence between subgroups of G and subgroups of H, which preserves both the orders of the subgroups involved and the subgroup inclusions. So this means that when you draw the lattices of subgroups of 2 isomorphic groups, then you can match them up so that you get the same picture, and also so that corresponding subgroups have the same orders. This is one property that I'm not going to try to prove, because I don't think the proof is too enlightening. And if you understood the proofs of the other properties in this video, then this one is not going to be too surprising to you. Anyway, I do want to give a warning here at the beginning, and this is something which comes up sometimes. And the warning is that the converse of this statement is not true in general. Now, it is true that usually when you find 2 groups that have the same lattices of subgroups, with corresponding subgroups having the same orders, they do turn out to be isomorphic. But there are actually examples of groups which are not isomorphic but which have the same lattices of subgroups. It's not easy to find pairs of groups like that, but I'll show you an example in just a minute. Before that though, I'd like to show you an example which is related to the property itself. So we've mentioned already in previous videos that the dihedral group of order 6 is isomorphic to S3. And even though we could prove that now, I'm going to delay the proof until the next video when it will be a little easier. But if you take this as a given for now, then it shouldn't be surprising, especially in light of property 7, that when you draw the lattices of subgroups of these 2 groups, you get exactly the same picture. And I've tried to choose my notation here in the generators involved so that you can match the 2 pictures up exactly. So the generator R here corresponds to the 3-cycle 1, 2, 3, and the generator S corresponds to the transposition 1, 2. And in fact, the map that maps R to 1, 2, 3 and S to 1, 2 uniquely determines an isomorphism from D6 to S3. That's something that I'm going to explain better in the next video. But anyway, for now, it's pretty easy to see when you look at these 2 groups that the lattices of subgroups are exactly the same, and that corresponding subgroups have the same orders. So this is a manifestation of property number 7. Okay, so finally, let's look at an example related to the warning that I gave you that the converse of property number 7 is not true in general. So for this example, I went through all groups of orders up to 16, and for all pairs of non-isomorphic groups of orders up to 15, there's no example of a pair of non-isomorphic groups which actually have the same lattices of subgroups. So in a sense, even though this example is pretty big, it's kind of minimal in the sense that you're not going to find a group with order less than 16, which does what I'm about to show you. So for our group G, let's pick the group C4 cross C4, which is a group that we understand pretty well. I can write it out using generators and relations as the group generated by A and B subject to the conditions that A to the 4th is B to the 4th is the identity, and that A and B commute with each other, so AB is B times A. Now, I'm not going to prove it for you right now, but this is a presentation of this group. Now, the group H, which we're going to use here, may not be familiar to most people, and it's something that I'm going to explain in a later video. So this group is a non-trivial semi-direct product of C4 with itself. And even though it's a little too early to define what this is at this point, I can at least tell you that a presentation for this group is as the group generated by x and y subject to the relations that x to the 4th and y to the 4th are the identity, and that xy is y inverse times x. Well, if you believe me that this is a group of order 16, then it's not too difficult to check that it's not abelian. And since G is an abelian group and H is not an abelian group, that means that these 2 groups are not isomorphic to each other. Okay, well, now I'm going to leave it to you to check that the lattices of subgroups of these two groups are actually the same, and this is something that took me a long time. But in the end, you're going to find out that the lattices of these two subgroups are actually the same, even though they're non-isomorphic. And in fact, not only do corresponding subgroups here have the same orders, but it also turns out that all corresponding pairs of proper subgroups in these lattices are isomorphic. Except, of course, the top two groups here. G and H are the only pair of corresponding subgroups here which are not isomorphic to each other. So this is a concrete example to show you that the converse of property number 7 in general is not true. Now, like I said before, it's hard to find examples like this, so usually when you have two groups that have the same lattices of subgroups, they do turn out to be isomorphic. But there are other examples like this as well, so you need to be a little bit careful about this. That's the end of this video. Thanks for watching. In the next video, we're going to continue and talk about how homomorphisms are determined by their values at the generators for a group.